Jai Shri Manan kids, I'm your Sridharsirphysics. Today we'll discuss the rod-wedge constraint. So what all it contains? Like a rod which can move along y-axis because of these two vertical walls. They are fixed walls. Okay, fine. Now there's a wedge. It can move only along x-axis. And there's a ground. This part is a ground. I will take the weight. I took the weight of the rod, 4 Newton. Weight of the wedge, 5 Newton. This is all set up. And these two are the walls which will not permit the rod to move along x-axis. These walls will make the rod to move along y-axis. The ground will make the wedge to move only along x-axis. So what is our entire discussion? We have to calculate the acceleration of these two blocks. So what is our entire question is? Find the okay, now they are in contact. You can see rod and wedge contact. Wedge is in contact with the ground. Rod is in contact with the wall. How do the normal contact forces will be acting? Now this will be the normal forces acting. This normal contact is by the wedge on the rod. This normal contact by the rod on the wedge. This one is this normal contact is by the ground on the wedge. This horizontal red color arrow, it is little bit value higher, that's why it is length of the vector is extending. This is exerted by the wall on the rod. Okay, these are the free body diagram. The forces are acting in this way. Okay, fine. Now, how do they will move? You can see clearly the rod is made to slide only along y-axis. Fine. And the wedge will move along y-axis. Okay, there's a basic constant equation what we have to generate here. How they are moving. The rod is moving along y-axis and the wedge is moving along x-axis. This is what overall the motion of the rod and the wedge will take place. Okay, kids, now we have to write the constant equation. Here the mg will be acting, weight m1g will be acting, the component of normal reaction and the acceleration a1. Here the component of normal reaction will accelerate the wedge. So for this we'll write the equations of motion, we'll solve it, and then I'll show the what is the basic constant equation. Okay, fine. Now how the rod is moving. The rod is moving along y-axis, wedge is moving along x-axis. What are the forces acting? Here this n sin theta will resolve it. Component of this will act like this. N sin theta, n cos theta. Similarly, n sin theta here and n cos theta. Then along y-axis for the rod, m1g minus n cos theta equal to m1a1. For the wedge, n sin theta equal to m2a2. How many unknowns are there? A1, A2 and normal contact. Three unknowns are there, two equations. We need one more equation. That was the basic constraint equation. Now how the accelerations A1 and A2 are related. Point A of the rod is in contact with the point C of the wedge. Point B on the rod is in contact with the point D on the wedge. As they start moving, you can see clearly now there's a relative acceleration along this direction and there is no relative acceleration in this. You can see clearly this one. The rod M1 will be moving vertically, wedge will be moving horizontally. You can see clearly here. This rod will be moving like this, where the wedge will be moving horizontally. There is one basic constant equation which is taking place. Now based on this, we have to write an equation. This will be common normal, this will be common tangent. Here I am showing that one. Acceleration of the wedge A2, acceleration of the wedge A2, this acceleration of the rod A1. I'll resolve this acceleration. A2 sin theta, A2 cos theta, A1 cos theta, A1 sin theta. Along common normal, the acceleration must be equal. Any reason for that? There's a wedge constraint. Acceleration along common normal will be equal if the two objects are in contact. There's a one basic condition. Acceleration of two surfaces are equal along common normal to be in contact. For the rod and the wedge to be in contact, their acceleration along common normal should be equal. This is a common normal. And this line will be common normal. And this what here. So here I'll resolve it. A2 sin theta should be equal to A1 cos theta. Here we'll write it here. One more equation. A2 sin theta equal to A1 cos theta. This is equation 1, 2 and 3. Solving all these three, we'll get the expression for accelerations of the rod and the wedge. The acceleration of the rod M1 is given by this formula after solving the equation. So the acceleration of the wedge is given by this particular equation. Now how that accelerations, how much they'll be related, let me show with the animation. So here it will be acceleration of the wedge will be 4.37, that of the rod will be 4 meters per second. When you substitute all the values, normal, contact, everything here and solving, we'll get these accelerations. Fine. This is one basic along with the accelerations, normal, contact, weight, everything all in the animations I'm showing it. Once again you can see it. In the ground frame, the rod will be moving vertically and the wedge will be moving horizontally. That is what is visible for you. Fine. Now in the wedge frame, a frame of reference Q, how the rod M1 will be moving. You can see clearly the rod M1 will move along the incline and there won't be any relative acceleration normal to the incline. There will be relative motion along the incline and that's what you can see it clearly. Fine. So there's a motion of the rod with respect to wedge. Now in the rod frame, how the wedge will be moving, that we'll check it. How the wedge will be moving in this direction. I will indicate it. You can see here in the frame of the rod, the wedge will be moving like this. Okay, this overall picture of the rod like a wedge constraint, which you need all this background. Okay kids, finally we are concluding the problem. I'll just show the last part of the animation. This is the motion of the rod and the wedge, and these are the accelerations for that corresponding weight. Fine. Hope everyone able to understand this rod wedge constraint. Please do like, comment, share, subscribe. So we'll explore the complete physics with this particular animations. Thank you everyone for great support. Take care. Bye.